Hello everyone, I'm Peter Campora, and I'm here to discuss our paper Taming Tape Annotations in Gradual Typing. So, a year ago, OOPSLA was hosted in the beautiful city of Athens, and I was presenting a paper on machine learning in C. And this year it's been quite the change in scenery, and it looks like OOPSLA is being hosted from my living room instead, or at least everyone's living rooms and workplaces, offices. So let's get down to business with this paper though. So we have a new kind of programming language process or paradigm that's being put out there called Gradual Typing, which aims to combine dynamic type checking and static type checking into a single language. So with most of these gradually typed languages are implemented by adding a static type checker onto an existing dynamic language. When we're just looking at these dynamically typed programs, we can see that the normal behavior of a program might be to concatenate and underscore to some kind of string argument, and that when we decide to change part of the program so that our argument went from being a string to an integer, at runtime we get some kind of type error. With these gradual languages, we'll start to bolt this static type checker on top of this existing dynamic language, and what will happen is that if I decide, or the programmer decides mistakenly, to annotate this s variable with the type int, and they should have been annotating it with something like string, then they will get a static type error because the string argument disagrees with the int annotation they specified here. And because plus is overloaded with the different kinds of types it can be associated with, it won't rule out int as kind of an invalid type annotation to begin with. So now it's just reporting the problem is with the string argument that's being received here. And this is pretty much what we kind of expect from statically typed languages. What's interesting about gradual typing, though, is that the programmers don't have to opt into adding all of these static type annotations to the program at once. They can leave certain parts of their program statically typed and other parts of their program dynamically typed. What's really interesting is about how the interaction between dynamically typed code and statically typed code should go. Typically, they allow dynamically typed code to produce values that flow into statically typed regions without giving some sort of static type error. So, if this is going to be allowed at runtime, then what should the value of this program be? Most gradually typed languages are have more of this behavior known as optional typing, where all of a sudden they're going to say that the program will just run like it was a normal Python 3 program. With sound gradual typing, however, a dynamic type error will be thrown that's different than the normal underlying dynamic type errors in Python 3. So if we're using this particular implementation of sound gradual typing in Python called reticulated Python, then this program throws an error when this 2 is returned from this identity function and starts to flow into this append underscore, which expects integers. So it'll say, oh, that string was not an integer, and I don't want it to infiltrate this statically typed parameter. So there are 3 issues here, though. One of which is that we can see from the previous program that the int annotation probably never should have been added to begin with. They should have specified that they were working with strings due to the fact that it was a program for appending or concatenating things. So one big issue here is that the runtime errors are good in that if they're triggered, the programmer can see, oh, I shouldn't have put an int annotation. Obviously, it should have been a string. But sometimes these runtime errors escape testing, and they can actually be put out into the wild, and this is a problem with dynamic typing in general, where all of a sudden your server might crash. Another issue is that unless you trigger the particular run of the program that gives the cast error, they might be adding more and more incorrect annotations to the program that also go unnoticed. So this incorrect annotation might lead the programmer to add many more incorrect annotations that they will have to fix later. And finally, in order for programmers, while they're doing this development process and gradually adding type annotations, for them to be confident that their annotations are correct, they need to trigger multiple runs of the program, or they just need to add types for everything, which kind of breaks the graduality that we want when using this gradual typing, that we can add annotations one or two at a time. So what we wanted to do with this work was to create a debugging tool with the following goals. The first being that we want to find these erroneous annotations that caused cast errors, and instead of reporting them at runtime, let's just try to be confident and say that we think this thing could be reported ahead of time. We want to determine what parts of your code base hid the annotation error. In the previous example, basically we want to report the identity function was responsible for basically hiding the error with the int annotation. And we want to suggest a replacement annotation. So for our previous program, we want to suggest changing int to something like string. The way that we're going to go about our first intuition in tackling this was to basically just remove all of the annotations from the program and the dynamic typing, and say we're just going to basically put type variables for all of these different parameters, and we're going to do some constraint solving to figure out what types should be given to these type variables, and we generate these kinds of constraints here where we look and say that, oh, a string maybe is flowing into beta when we're trying to solve constraints for this application over here, and then the beta flows into alpha, so this looks like beta and alpha maybe should be strings or something like that. But then we see that this string differs from the fact that before we were using this type variable that this s was annotated with int. So we find basically some kind of conflict between inferred types and the original annotations for the program, and this kind of leads us to saying that if the inference disagrees, then maybe we should suggest to the programmer that they change their annotation from int to string unless they're really confident in their annotation. So our overall approach started to look something like this. Take a source program, do type inference, collect all the different kinds of annotation and inference conflicts, report these conflicts, and one issue that we ran into was that traditional inference can be too aggressive. We had to start dealing with all of these dynamically typed idioms that were hard to do inference and type checking with. And moreover, there was just too much being done with trying to remove certain kinds of parameters. We wanted to just explore what happens when maybe you're only removing a couple of parameters at a time. So we used this variational type inference from earlier works to kind of do this enumeration process of only removing or inferring types for a couple of statically typed parameters at a time. So this exploratory typing basically introduces these things called variational types, which we have two different kinds. We have the static variational types that are basically they have this subscript to say what unique one they are, and an S to indicate that this variation was introduced by a static type annotation on a parameter. And we have these dynamic variational types to say that these parameters were kind of unannotated, and that in both cases, on the right-hand side of both variations, we're saying that this is the type that we have inferred for this, what we think this parameter should be annotated with, and ideally for this dynamically typed function, what the inferred type should be if we were trying to type it, so that we should have some kind of polymorphic function over here, and beta 1 is a type variable. So when we're doing this to try and solve, we're using the inference process to then try to solve what things are going wrong, we will generate constraints to solve something like this application over here, and we might generate these kinds of constraints. The relation right here is known as the compatibility relation, it's just the normal consistency relation on gradual types, but lifted to also handle these variational types. And note that this star right here is the dynamic type in our representation. So, all of a sudden we have these compatibility relations that we need to solve. This is done by realizing that this variational type is really encoding the idea of having two separate types for this dynamically typed identity function parameter, x. And one of which was that over here, it has its original dynamic type, and the other being that we're trying to move it to use this polymorphic type, and in which case we need to instantiate the type variable so that it's now has type string when we're returning and doing the rest of the kind of constraint solving process for this program. So with that, we can use this kind of substitution over here and replace the instances of beta1 with string, and we have this complicated variational constraint with variations on both sides for this compatibility relation, which means that this is encoding two different types for the statically typed parameter s, and this was two different types for the dynamically typed parameter x that we need to see if they're consistent. This leads us to a total of 4 different basically consistency checks that we need to carry out. This one passes just fine, so we use this top to indicate that this kind of innermost constraint succeeds. On the other hand, int is not consistent to string. These are two different static base types, so this relationship does not hold, whereas these two do. Notice that this corresponds to when the dynamically typed function now has this inferred type, but the original static type annotation for s remained. So we can now basically put these results for our different projections of solving these compatibility constraints back into a data structure. And what we want to see is that this bottom being in this position where it was on the left-hand side of s and the right-hand side of d indicates that we discovered an error when we inferred a type for x, the identity function's parameter, but left the int annotation. Basically, then we saw that string disagreed with int and that there was a problem. So we now know that d, when it's left dynamically typed, because there's two tops over here, masks the errors that were present when we removed it and inferred a type, and that because this is on the left-hand side of S1, that the int annotation was a problem, and that we can find a fix by going to this top over here, which corresponds to changing the int annotation to string. So with this pattern, we could basically support all 3 of our goals. In the full paper, we introduce more kinds of variations for dealing with things like dynamic features like eval and variations to reason about conditional branching. We present algorithms for analyzing typing patterns and suggesting possible fixes and supporting our different goals. And we present an evaluation that basically we randomly seeded cast errors into different Python programs by using a tool to add incorrect annotations. And then we found the errors by using our tool PyHound, which implements exploratory typing, and discovered all these different errors, reporting them. So you can see the full evaluation details there. A little bit of self-promotion. I'm graduating. I have, a decent amount of OOPSLA papers. This is my 3rd OOPSLA paper at this point. I'd like to get ideally an industry job working on a gradually typed languages so that I can kind of really test putting these techniques on real issues. And I'm also considering academic jobs. So if you think my work is interesting and you know of some openings, please contact me at either my university email or my Gmail here. Thank you.